All right, up and running. Here's another attempt at a video without any preparation. But I was thinking about, I was talking with a colleague about implicit and explicit differentiation. And, I think so. This video is probably for folks who have maybe even completed the first half of a typical calculus course, which is differentiation. I like to teach them at the same time, differentiation and integration, they're inverse operations. But hopefully this might deepen your understanding of something you've worked with mechanically. And if you haven't taken any calculus, I'm a big fan of starting conversations. And I think that the initial part of this video would still be very helpful to start thinking about some of those initial concepts, where they spring from. And that'll help you down the road. All right, so let's, that's a pretty ugly square. So let's see, I've got to come back a little further here. I've got a chair in my way. Let's hope that's enough. Move chair. Can we see these table values? Yeah, we can see them now. All right, so just some, some geometry here. -1 times -1, 1, 0 times 0, 0, 1 times 1, 1 unit area. 2 times 2, 4. We're pretty familiar with the squaring process. And it's good to start initial concepts someplace that you have a feel for. Okay, and what I'm going to look at here is change. I'm looking at y2 minus y1. And I'm looking at x2 minus x1. And that is our definition of slope. And so I'm squaring, I'm just picking 0.001, and I'm squaring it. You don't need a calculator because it's some nice patterns. And I get 0.06 decimal places, right? 3 decimal places turn into 6 when you're squaring. It's not changing much. But as I get bigger areas, I start to see a little bit of change. 002, 001. And when I get to 2, I see 004, 001. And if I look at it geometrically and I get to 3, we get 9. Well, you might even be able to guess what 3.001 gets you. It turns out it gets you, and you can stop the video on all of these, right? Pause. Anytime I say something and I ask a question, you can always hit the space bar and pause and think about it for a little bit. So this is 9.006001. So I decided to draw that in my 3rd grade skill set. And looking at it, I mean, there's some error here, right? And that error is the 0.001 squared error. But the area seems to be, and we can always describe the area as a difference in y's, y2 minus y1. That's a difference in y's. It doesn't hurt to think of it that way. And it appears to be 0.003, which comes from 0.001, which is really your change in x, times 3, which is the length of the side and square we picked. I can show you here easier. Right? And there's 2 parts to it. 0.001 times 3. And that change in y is equal to 0.006 times that change in x. Which kind of looks like y2 minus y1 equals some multiplier times x2 minus x1. And when you zoom in on a curve, it looks linear. And based on this calculation, it appears that the change in x divided by the change, the change in y, which is roughly at 3, the area is 9, and the change is roughly 0.006,001, 6 to 1. And at 0, it's really the first 3 digits were 0 divided by 0.001. It's not changing much. Why isn't it changing much there? Well, if you go back to these geometric looks, if there's no square, and we're really looking at like 2 sides of a square. Well, if you don't have one, you don't have much to work with. And that's why this has a minimum rate of change right here, magnitude wise. On the left side, we'd be coming down. You know, if we did the -3 gets us 9, and we did the work there, you'd actually be coming down at 6 to 1 ratio. I'm not gonna throw the table values up there now. But we're getting towards the discussion about implicit. You're probably wondering, where's this going? But I think it's important that you really make a connection here as to the origins of the derivative. Because this is basically what Newton saw. Newton saw a 3x3 and he inscribed a, 2.99999 size triangle and a, well, it would have been bigger, and a 3.001. He sandwiched the 3b3 and got himself a nice accurate 6 to 1 ratio. After teaching calculus for a while, and before seeing the sandwiching, that probably should have gone back and looked at the origins of what he wrote. It saved me a lot of years of thinking. I saw it more as a layering process, which is what integration is. Each one of those layers is actually a derivative. All right, so where are we going? So squaring is side length to area relationship, and square rooting is the inverse. Right, so we go from side length to area, or we go from area to side length. Side length 0, 1, 2, 3, 4 gets us area 0, 1, 4, 9, 16. We can kind of see that the areas are increasing numerically faster than the side lengths. So it's nonlinear. And if we reverse that, we would start with area, and we would still get, growth. It would just be slower. So here's our signature x squared, and here's our signature square root of x. As x's get bigger, it's hard to think about it magnitude wise here, but -9, +9 to 4 to 1 to 0. Remember what the x's are. -3, -2, negative. These x values are getting bigger. Magnitude, they're getting smaller. But let's just think about this starting at 0 and the areas of 1. I gotta make that smaller. 1, 4, 9, 16, so on and so forth. It takes more area to get a jump of 1 unit. All right, rambling a little bit. Let's get to the heart of this video. Linking up implicit and explicit differentiation. All right, so one of the examples I'm going to use is the square root of x. All right, the other one I'm going to use is x squared plus, well, I'm going to start with x squared plus y squared equals 25, right, which is going to be based eventually on the derivative of the square root of x. All right, so from your algebra 1, the square root of x could have been written as x to the 1/2. And the derivative of x to the 1/2, which is really that dy dx, that process that we were talking about over there, from a power standpoint is 1/2 x to the -1. And from your algebra 1 studies, you should be able to see that that is 1/2 root x. All right, it's the square root of x in the denominator. Okay, all well and good. And if you've already studied derivatives and you've done the chain rule, then you know that if y equals the square root of f of x, then y prime, I'll go to y prime notation, then y prime is the derivative of what's inside divided by 2 times the square root of what's inside. That's what I ask my students to memorize. I think you work with this so much that it's important to know that form. So keep this form in mind. We're going to work with it now. We're going to look at explicit differentiation over here. The problem we just did right now was y equals the square root of f of x, and explicitly we get y prime equals f prime of x over 2 times the square root of f of x. Let's link it to implicit differentiation with an actual problem. Okay, let's look at y equals the square root of 25 minus x squared. By our definition, y prime is the derivative of what's inside, which is minus 2x, over 2 times the square root of what's inside. Okay, obviously the 2's can cancel, and we'll do that in a moment. All right, let's look at that from an implicit standpoint. And I don't think that with the strength of computers now, folks might recognize that. I don't think probably doing it as often as years ago, but that's really the top half of a circle, where we're starting with x squared plus y squared equals 25. All right, if I solve this for y, then I get y squared equals 25 minus x squared, and y is equal to plus or minus the square root of 25 minus x squared. So the positive one is the top half of a circle. I'm hoping you studied this algebra 1 and algebra 2. Okay, so what's the differential? I'm sorry, what's the implicit differential process here? Well, we're looking at really the geometry of what we looked at the beginning of this video. X squared change is dictated by 2 sides of the square, and that dx, remember, was our 0.001. Okay. Y squared is just a different variable, 2y dy. And 25 is a constant. If you see it changing, give me a call. I figured out how to let people make comments now on the videos. Feel free to comment and say, hey, you know, I'm seeing it change. If so, we should have a little communication. Right. That's not changing. All right, so now it's just algebra. Right? If we want to get dy dx, then you got to divide by dx. You got to divide by dx. You got to do it to each number, each variable situation, or you've broken a rule. All right, I guess I should have just put that here. There, that looks better. And now I've got what I'm looking for, provided I move everything to the other side. And if I do that, the first thing I'm going to move, the x cancels here, is 2x, which is minus 2x. And then I'm going to divide by 2y. And that's going to get me dy over dx. All right, so let's do our linking now. Let's get rid of the 2's, the same way that I could have over here. Okay, so I'll use the eraser now. That gets me minus x over the square root of 25 minus x squared. And over here, I get minus x over y. So let's put them together. Okay, so what's the link here? Well, go back to the beginning. What's another name for y? Okay, so that's really linking them up from a mechanical standpoint. And now that we've done that, we might even, I'll call it our first link. We might sit down and think about it a little deeper level and see what other relationships we see that come out of that. But that's a first step. Now we could do this with some other function, so why not? Why not think about y prime equals ky? For those of you who have got some experience with calculus. So what's that saying? Well, it's really saying that you've got a problem like y equals e to the 5x. Okay, so what's the derivative? Well, it's the derivative of, the derivative of e to the f of x is f prime of x times e to the f of x. It's a shortcut. So what's the derivative of 5x? 5 times the function e to the 5x. Well, I think I'm seeing a y prime equals ky type problem. What was y? to the 5x. Right, so that's your y, and what was your k? 5. So open your CPAT. And if you've studied the exponential process, where y is some other value other than 0, it's like 4, then you can up this to looking at y equals, let's just do one, y equals, yeah, let's actually do it from the algebra 1, which is in algebra 2. We've been studying this. So let's look at 4, let's look at 1950. I don't know if I want to do this right now. I'd do this on my own time in case I make a mistake. I'll come back and put an addendum to this. But let's look at y equals 5, y minus 3, and let's talk about, well, let's make it 5x, right? So we've got this, and we want, this is the derivative, and it equals that. And let's start with 0 gets us, let's make this even. I think it might be easier for you. So let's make a 0 gets us 20. Okay, and so what I believe our answer is, and we'll get it, is y equals 20. So I got to have 17e to the 3x squared plus 3. Okay, that should be the answer to this. All right, and where do I want to take it? Oh, I'm going to take it from here. All right, we're going to look at the derivative of this, and then we're going to see if it actually does fit that form. I haven't done calculus in a few years, so a little rusty. All right, so what's y prime? It is itself, exponential functions are derivatives of themselves, times what? Times the derivative of the functional part here, which is 6x. Okay, so what's another name for 17e to the 3x squared? Well, I think we got to go back to this line of work and we go, oh, that's y minus 3. That's what 17e to the 3x squared actually is. And so there's our y prime equals 6x y minus 3. Okay, just trying to link the explicit differential process to the implicit. Right? Okay, so I should be able to work backwards from there, and I probably should, but I'm going to save that for another time because I'm tired. And it's still morning here. All right, so hopefully I'm rambling here. Hopefully that some of that gives you some things to think about, especially if you've already finished studying derivatives. Just puts another spin on it. And if you haven't studied any calculus, I do think those tables at the beginning of the video are things you should think about. All right, have a good one.